Yes,
Then only the instruction will be reached to the organizing people.
Am I audible, Mahipal sir?
yeah, yeah.
Yeah, actually, my name is reflect in a presenter. So, if it is possible, kindly change my mode as a attendee.
Yeah, sure.
Yeah, my name is reflected in a presenter.
Yeah,
So, I request, will you please change the mode?
yeah, yeah.
Thank you.
So Vijay sir, now we have made you the presenter. You can start your presentation. Sorry for the delay and the session.
Not a problem.
And
Sir, can you just mute yourself once?
yeah, yeah, I'll mute myself as well as I'll mute all the other
Yeah.
students, other
Yes.
participants as well.
Done, sir. Hello, everyone. Good evening. Good morning. Sorry. Good morning. So I'm Vijay Shanthagiri. I'm from Bangalore, and as Mahipal sir introduced me, I have a small startup in Bangalore and a second startup which is recently just called Certishort.com. So today I've been invited to give you a glimpse or an introduction to machine learning and AI, and I'm pretty sure that yeah. Before I start, I would like to get some chats whether I am audible, whether the audio is clear, or do I need to do some changes in settings and stuff.
Yes, your audio is clear, sir, but the chat
Okay.
box is mute, so we can't able to chat.
Okay. Yeah, I would love that to have it opened. So
Yeah,
Mahipal sir,
we
if
are
you can
we are
just.
working on it. Sorry, we are working on
Okay.
it. We'll do
Okay.
it in within a few minutes. Just
Done, sir. Done, sir. Absolutely. Okay.
By that time, you can just unmute yourself and you can ask questions if you have.
yes, sir. You can continue, sir. Thank
Done, sir. Just let me share the screen.
Oh, oh.
Okay. All right. So I'm guessing that the audio, video, the screen share is visible.
Yes,
I've just
serviceable.
shared the screen. Perfect. All right. So now we know that this FDP is on industrial applications of machine learning and AI. And as I've seen many different speakers out there who's going to be presenting many aspects of applications of machine learning and AI. And with that context, it is very important to understand exactly what is the gist of machine learning. We can be led astray. We can have a lot of assumptions, and with the learning, we can have a lot of our own biases involved when we understand machine learning. So I've put together a presentation which is going to walk through from the beginning of what data is and how the uh, the field itself has evolved out of the graduation in terms of abstraction in machine learning, abstractions in mathematics and stuff. So while you follow all this through, we'll completely loop and summarize the whole field so that the sessions that are going to follow later will make a lot of sense, and there'll be direct connection with the subject and the application areas while you're listening to other speakers speak on ML and AI. So with that, let's begin. And of course, I really want to thank MUJ and the team to have given me this opportunity. And everyone is free to ask questions. If there is a urgent question that needs to be addressed, you can just raise hand and prompt me to address something. If not, we'll have a Q&A session at the end of this presentation. Let's begin. First things first, it's all about data. Machine learning, artificial intelligence, data science, data analytics, predictive analytics, statistical learning, the gist of all of this is the same. First thing, how much data do you have? Second thing, what is the quality of the data that you have? Did you simply collect data somewhere, or did you actually do a data science experimentation? Did you make sure that enough demographies, enough classes of variables were identified before you collected the data? All of that matters eventually in you getting the right model using which you can predict the future events. With that in mind, let's begin the journey of understanding what data is. So, of course, data comes from observation. When you observe the world, when you observe something on which you want control, when you observe something of which you want the maximum control on, and you want to automate it, and you want to be able to be ready for all the contingencies which are not projected by your usual systems. If you want to be ready for it, at least if you want the system to give you 5 minutes of its own intelligence and stability before you act, if you want that, then you want to build a machine learning and AI model. To be able to build that, first you need to understand the types of data, and it's a very uh, robust, a very neat classification, classifying data as quantitative and qualitative. Now, quantitative is data that can be measured with numbers such as duration or speed. Basically, it's everything that you can put in terms of numbers. You observe the world, you ask a question, how many corona cases? Numbers. You observe the world, you ask a question, how severe was his case? Usually you don't get a number directly. Maybe there is a measure of severity deep inside the medical dictionary, but it is not something which is easily accessible to the population. If, of course, a statistician and a medical doctor and a virologist are conducting an experiment, probably they would use a set of observations to coin a new term called severity. Then severity will become a quantitative data. For all other cases, if you ask how severe, you have answers like not so severe, very serious, all these kind of answers. These are not directly put on the number scale. They are qualitative. Now, inside qualitative, there are two different categories. We'll see that. While first we'll understand the quantitative nature of data. Now, having reduced an observation in the world to numbers, you have two kinds of events itself. One is a discrete event, another one is the continuous event. So discrete events give rise to numbers which are discrete in nature, like whole numbers that cannot be broken down. such as number of items. Or if you want to ask a question, how many times Virat Kohli has won the toss, you will never get an answer like 32.5. You'll never get an answer like 12.8. It doesn't make sense. It has to be a discrete number. So that's what discretization is. That's what discrete means. And the same thing when you want to talk about a number that actually can be broken down if you want to be more and more accurate. For example, if you ask yourself how many liters of petrol you have in your car right now, if you just want to approximate, you will say 2 or 3 liters. But if you're really questioning it because you want to know how far is the next petrol bunk, you would want to go and get deeper into the approximations, in which case you would use the decimal number 2.3 or 4 or 5 liters. It's up to you, like how you assume it, what measurements you come to. But if you want to really get accurate, and if you want the decimal systems to work over there, that's when the numbers get continuous. There are certain areas where you will usually find these, but these are the usual ones. These are the usuals. This is what there is always. This is the special case, the discrete events, where the events itself will not allow any decimal numbers. For example, the tossing was the one. Another one is how many items did you buy from your favorite shopping app last year or this year? You'll never tell me a decimal number because it doesn't make sense, right? So that's what it means when I say discrete and continuous. These classifications are very important because the moment you find a particular kind of data, there are certain algorithms which fit well in predicting those kind of or building models using those kind of data. Okay, so that is the reason why there has been a very watertight logical classification where there is no ambiguity in the definitions. So I hope you will pay attention to these things. Now, I was talking about qualitative. So it says non-numerical data that is categorical, such as yes or no, very, too much, how was the movie, good, bad, ugly. All these things are representing categories, emotions, right? Now, in qualitative, there are two types, nominal and ordinal. Data used for naming variables such as hair color, what kind of laptop, what kind of pen, nominate. You're nominating something. However, if you ask a question, how severe is the corona case? You have answers like not severe, very severe, very, very severe. Now you already see that there's an order here. You can actually arrange it as ascending or descending. There's an order. Even if you have a qualitative nature of categorization of the event observed, if there is an inherent order in it, that is ordinal. Okay, and this, like happy, neutral, unhappy, 1, 2, 3, you can name it, you can give a number to it. The same thing doesn't apply to religion. How many different kinds of religions representatives are here in this FDP now? You might be from different religion. Now, just because I started collecting from one to the other end, I'll start writing some religion. I cannot number it. I cannot number it. Just I can give a serial number, but it doesn't mean that one is bigger, one is higher, and one is lower than that. So it doesn't make sense, right? Because there is no logic to it. That is the meaning of ordinality. This ordinality plays a big role in building machine learning models. Next, under continuous. This is the crux. This is where all the things happen. Under continuous, there are two kinds of data, interval and ratio. Now there is continuous number. You've been observing something, you're getting some continuous numbers. What do you have in this series, the number series? You've got some intervals and you have some ratios, which actually which helps you to predict the next number, the arithmetic series, right? So numbers with known differences between variables such as time. So on x-axis, you always represent time because it is independent. So you can say weeks. The moment you say weeks, you already know. Let's say I mark this time axis, and I call this. Let me call it week. So automatically, whatever I've marked here, it means that if it is week 1 and is week 2, I need to have 7 units bifurcating this because the week has 7 days. Or if I just say day, then probably I would decide on whether I would want to break it down into hours or minutes or seconds. But the differences are known. This is a this is something where you import the system which has been developed for our own use. Weeks, days, the time zones, and all of that has been created by humans. And all this interval data comes here. Now, if there is no interval data, if there is some other value here and some really random numbers have been positioned on your axis, you can still go ahead and find if there is a ratio between a number x1 and a ratio, if there are numbers x1, x2, and x3, you can actually go and find that if there is any common difference between these numbers, so that using that common difference or using that pattern, we can project what could be the next. But those ratios are important. So overall, these are all the types of numbers that you will deal with any which way in all of your machine learning, AI, data analytics. These are the numbers. Moving ahead. Yeah, anybody's got a question? I just heard somebody unmute. No? Okay. Now, when it comes to the computational aspect of data, of course, when you want to observe, after observing, you want to store the data somewhere. It is about a certain kind of data. So when you want to look at data in that way, in terms of where you observe, where the data came from, the classified data in terms of its structure and source. Okay, structure and source. If you want to, this is a general classification based on its nature of the data. This is a classification or just a bifurcation in terms of the class. Here, the bifurcation is based on structure of the data and the source from where it was observed or taken or sourced. So one, of course, is the structured data. Somebody gives you a very neatly, nicely tabulated Excel sheet. This happens usually in banking, that they have collected everything so neatly that when the data is given to you, it is already structured in nature, and it's just a clap to apply and get some results. Now, of course, there are unstructured data as well. For example, if you go and talk to an astronomer or a space researcher, the kind of data that comes to the radio astronomy, radars, they're all unstructured because the universe is not sending you out structured data so that human intelligence can fathom and understand what is the secret of universe. It doesn't work like that. We have to devise our electronic systems in such a way and our data science pipelines in such a way that the given data has been collected properly and then filtered through, and then a proper model has been built. These are all unstructured, so there's a lot of challenge in restructuring this data so that some intelligence can be derived out of it. Now, same thing if it is a geographical data, it's called the X, the Y's, the latitudes, longitudes, position, a lot of data that is sourced from geographic locations. And of course, there is one more kind of data. If the same data comes live to you and it is not like given to you as a database already, if the data is coming to you live, let's say from here, live, Of course, in this way, first they will collect it and then they will structurize it and then apply. But there are cases, let's say in
Vijay sir, sorry to interrupt.
yeah.
Yeah, sir, actually, from 11 o'clock, we have an inaugural session by AICTE. Okay, and the participant need to attend that session as well. So we would take a half an hour break, okay, from this session. Meanwhile, the students would attend that inaugural session, and we will come back and restart at 11:30. Is it fine,
Okay.
sir?
Yeah, it's fine. It's fine.
Okay, and sorry for the.
Yeah. My session though will be for till 12:30, right? After that, I get 1 hour.
Yeah. You can get now.
Okay, there's a lot of ground to cover. So, anyways, thank you. I'll meet you after.
Extend the session as well a little bit if required at that time.
Done, sir. Done, sir. Thank you.
Okay, so I will request the participants to please join the session. The link has been shared in the WhatsApp group. Okay,
so my this one will be logged in. Okay, let it continue, or should I off it and then come back?
No, you can keep it logged in, sir. You can keep it logged in, sir. Not an issue.
Okay.
Not an issue.
Okay, sir. Okay, sir. Thank you.
You can stop the sharing. Otherwise, you can stay logged. Yeah.
Done,
Thank
sir.
you.
Thank you. All right, people. Thank you. I'll see you at 11:30.
Thank you, sir.
Am I audible? Why, sir?
Yes. I'll share
Yes,
the
sir.
link in the chat, in this chat as well, and I will add you in the WhatsApp group as
Yes,
well.
yes. Thank you, sir. Thank you.
Okay. हमारे मेकाट्रॉनिक्स वाले फैकल्टीज को दे रहे हैं कि नहीं दे रहे? मेकाट्रॉनिक्स वाले फैकल्टीज को दे रहे हैं कि नहीं दे रहे? बोला नहीं ये पर नहीं आप तो करके रखो. Hello. Am I audible?
Yes, sir. Yes, you are audible.
Okay. Vijay sir, are you here?
Hello.
Yeah. Good.
Am I audible?
Yes, sir, you are audible. I'll make you the presenter.
Okay.
Okay. And few more things before starting the session. We have added most of the guests to the team. So I hope most of you would be able to put it on chat. Okay, you will be able to access the chat. And
Chat in channel meetings is only available to learn to team members.
Access chat.
yeah, so we are slowly adding everyone. So by 10-15 minutes, once the session starts, we will add everyone to the group. Okay. And now for the timing, I'll make Vijay sir as the presenter. And one more thing is, before ending the session, we will be sharing a feedback link and an attendance link. Okay, and the feedback link and the in the chat section itself. As so it is a compulsory to please submit the feedback and the attendance form. Okay, so that because we need to submit it to the AICT, which will give you the certificate. So it's very important to make this available to fill up this form. Okay, so before leaving the session, please make sure that you fill up that form and you complete that attendance, both the attendance and the feedback form. Okay. Vijay sir, are you able to?
Yeah, I can hear you. I can see that I can share my screen right away. So I'm doing it right away. Okay, so the screen has been shared. Welcome back to the session which was discontinued, and hope you guys had a great inaugural session out there. So I was talking about the structure and the source and a lot of different kinds of data. So let's just summarize. We've just begun what is data, and we had a complete understanding of different kinds of data and why the classification is important. Another classification
Yes, sir.
was about
I
the
think
structure
your
and the source.
We cannot see the presentation, sir.
yes, sir. We cannot see the presentation yet, sir.
Okay. Why is it so? Stop sharing. Tray, open, screen to share. So I've just shared.
Still not visible, sir. Still no.
From my end, should I log off and log in again? Should I?
So try that way because sometimes
Yes,
it
yes.
happens that.
I'll do that. I'll do that. Okay, I have just shared it again. Hope it's visible now.
Sir, it is sharing the Teams screen, not your present. Yeah, now it is.
Right.
Yes, sir. It is visible now, sir.
Thank you. Thank you. Okay. So this is just a small slide here. This is the kind of data that I used to work on. when I was in the industry before starting my own firm. So that was about spatial temporal information system. So all the data that is in real time and real time analysis and real time analytics of all these assets, the military and space assets which were there. So this is the kind of data that we were handling, and we did a lot of good work with this kind of data. So it was really fun, a lot of learning, and that's how I completely got into machine learning and AI, and especially in the real time analytics zone. Well, let's begin. The next part that I want to address is the journey of data, the journey of mathematics itself in the context of machine learning and AI, which is you need to have a story, because we need to have a story behind how the whole thing fits. So that's the reason why I put this small um, uh, journey out here. We begin with first the appreciation of the fact that human brain is a reverse entropy engine. So of course, when I say entropy is the measure of disorder of a system, measure of disorder. And human brain, it's very important when you are trying to understand artificial intelligence. First, we need to understand the secret of intelligence itself. And somehow, by nature, the design of our brains, the design of our minds are in such a way that we actually tend to reverse this. And that's what was happening here. We had some disorder uh, in the system, like we had noise and stuff, but we figured it out. We figured out a way to remove noise. We have the solutions, the reasons for it and stuff. So human brain being a reverse entropy engine has always been the case. It has always been the, so somebody needs to mute. Okay. It has always been the case with this kind of a setup in the brain. The human being evolved, and the first problem this reverse entropy engine would encounter is when you go back in prehistoric times, the first problem that was there was the problem of counting. When life is when life is
Named their device as 81 underscore me, right? Like roll number underscore me. Some of the students have named their device as ID.
Sir, somebody needs to mute, sir. It is really annoying.
And some of the students have named their device as
Mahipal, sir?
learning. So what I request to all my dear students,
Somebody is taking, somebody,
roll number underscore ID underscore me. Roll number underscore ID underscore
is there anyone who's attending? Is there anyone who's from the organizing team here? Hello?
Yes, sir. Yes, sir.
Sir, somebody needs to mute because somebody's mic is on and there is something going on in the background.
I'll do.
Sorry, gentlemen, ladies and gentlemen, because of that issue. Well, so problem of counting. We go back in time, we understand, we observe what would be the life of the prehistoric people. And life was simple. They just had a few objects to control, few objects to handle. So there wasn't much need of reducing, because everything was handleable just on your fingers.
That हो
The
गया sir.
idea of one, the idea of two, an idea of many. This is it. This is all the brain could fathom. But as life becomes complicated, when there are too many items, when life becomes more and more out of control, you need a system. And human beings developed the system of numbers, identifying and representing, nominating objects with certain symbols, and those symbols evolved and became a number system. So inside number system there are a lot of patterns, which of course when they created the number system they weren't aware of it. The number system is a very innocent system. Starts with nothingness, then a symbol for unity, then a symbol for two unities, another symbol for three unities, and was very innocent attempt. But inside this, because of this repeating pattern, there are a lot of patterns, and the number theorists, they work their life and they enjoy this process, and they come up with different a beautiful series out there inside that. So we are not going to delve into that, but we just want to appreciate the fact that there is a lot of beauty inside the numbers and the patterns. So we've got the prime and the composite and a lot of other stuff inside. Now, moving on, when the numbers became a commonplace and life became more complicated, because once you are able to understand the world with numbers, you're able to do much more things. When you try to do much more things, life becomes more and more complicated because you have more things to deal with. So in that situation, a newer representation system evolved, and that gives rise to the number series, where mathematicians would actually put an equation out there and represent what could be the next number that would come as an algebraic system. So that number, see, this was the beginning of that algebraic system, as counting evolves as a system to represent a series of numbers. Now, the next question that was begged to be asked was the question of areas. You want to answer questions like, what is mine and what is yours? For a prehistoric man, for a prehistoric being, the beginnings of civilization, they had the first encounter with understanding how much is yours and how much is mine in terms of area. So, of course, people came up with a very smart solution. Let's take length and breadth, and let's put length, breadth, number of times, and then whatever the number comes up should represent this area. If the area is bigger than this number 1 and the new area of number 2, this num1 will be less than num2. Okay, so it was just a representation. But the actual problem was when you had to deal with these kind of shapes. In fact, these kind of shapes. How do you find an area for this? Where will you find length? How many times the length and how many times the breadth? You're not able to even define it properly. How many triangles can you shape it into? It's not possible. So that's the reason, that's how a newer system for calculation was required. And of course, this led to nothing but the area under the curve. And you take the difference, a small infinitesimal derivative, and then integrate it over the curve. That's what gave rise to calculus. Okay, so this is very smart move, fantastically done. The next problem was when things go even more complicated is when people start moving around, and then a definite system of direction was needed, and that gave rise to coordinate system. These coordinate systems are of different kinds: ellipsoid, center point, and the one which is the Cartesian coordinate system, which has x, y, and z, and the one which has the longitude and latitude. So there are two different ways of representing an exact point on Earth. So if you just want a point on the circumference of the Earth, then you would want to take it. You can reach that point in terms of latitude and longitude. Okay, so that is one major abstraction that evolved out of these things. Now the question that actually gave a breakthrough in terms of intelligence is when the people devised a system and they asked the question, let the number be x. With just this small supposition of let the number be x, you can now do a lot of reverse calculations by modeling the phenomena. This is very simple. If you want to find the highest common factor, if 9 is the highest common factor with 45 and another number, you can find that number. So let the number be x was a beautiful abstraction that gave rise to intelligence. And with that, came the question, how much of X? So again, let the number be X is fine. But when you want to answer how much of X has changed, that is actually the real application of calculus, where now the earlier one was just a simple application of calculus. Now this one will be differential calculus, the partial differential calculus, and all of that, partial derivatives and stuff. So this is used extensively in finding your optimal solutions in machine learning. Very important. Now, the next question that was begged to be answered was, first we had let the number be X, then we said how much of X. Now we ask, is there an X? How much is the probability that an X actually exists? Now that
कुछ नहीं है.
is dealt with probability. So you would want a system which can give you certain measurements and tell you how much on a scale of impossible to certain is the event that is described falling into. So probability, as you must have known, is P is favorable outcome by total number of outcomes there are. But this is a very simple definition. In machine learning and AI, we deal with conditional probability. It's not just what is the probability of a certain favorable event occurring, and then you will calculate it by the ratio of the favorable events by the total number of events. But in our case, we would want to calculate something called conditional probability. It's not just a simple probability. It is about what is the probability that something will occur after something else has occurred. So A and B are events here. If you say this is the naive Bayes equation, so this is a equation for conditional probability, and the probability of event A occurring provided event B also has occurred is probability of event B occurring after A occurred into probability, all our probabilities. Okay, these probabilities can be calculated because the data will be there. Data for event A, data for event B will always there with us. Using those, we will calculate the reverse conditionality and the probability of occurrence of the event A itself independently and probability of occurrence of event B independently, and we get all these values, and whatever the number comes out, that is the conditionality. There is a beautiful proof for this, and people have written papers trying to discredit it, but it has come out and been successfully applied everywhere. Now, all of this having said and done all of this, the fundamental focus should be on statistics, because it's all about numbers. And whatever here I've shown you, whatever applications that are going to happen, all of this that has been addressed here, everything boils down to data. And as I was talking to you about the gist of interval and ratios, the system which is going to bring out this, the hidden truth in the number, the hidden truth in the data, not a number, because that's in fact what I wanted to say. Statistics is not about the numbers. It's about the relationship between numbers. Because if these numbers represent an event or some phenomena, the truth and the nature of this event and phenomena is hidden not in the specific number that is a part of this. Like, let's say it is not about a salesperson Fuller who got an order of 1,440. This is not what we are interested in. We are generally interested in the complete sales process. So we are interested in the difference between these numbers. So once these numbers, the difference between these numbers and a different system of appreciating the difference, the ratios, the drifts, the range, the frequency, the variance, the standard deviations, all of this, which are there inside this number. So that statistics is the one which gives you all that. So you can have the number, you can have the mean, standard deviation, range, skewness, kurtosis, coefficient of variation, all of this. This is a beautiful field of the statistics. And of course, whatever you see here is only a part of this descriptive statistics. This is where it begins. Eventually, this moves to Mahipal sir. Am I the only one who's hearing this noise, or is there anyone else? Is it just
So I'm
You are
muted.
hearing some disturbance, sir.
There are a lot of noises. A lot of noise is there.
Yes, sir,
Yeah,
we are hearing some background noise.
I've again muted everyone.
Sir, organizer can mute everyone, sir.
Yeah, I've muted. Sir. I think now the noise is gone, sir.
yes, sir, yes. All right. The disorder of the system, right? Right. All right. So descriptive statistics, I was telling about these numbers, these statistical numbers are just the beginning. Okay. These are just what are just the first attempt or the first phase of making sense of the numbers. This is where it begins. Eventually, you want to be able to do inferential statistics, because once you describe the data, what is your inference from this? Now, machine learning has a lot of connection with inferential statistics. Once you build a model, you want to know how true your model is. And there is a lot of stuff. So we'll come to that. In fact, I'll tell you, there's a lot of stuff because of the limitation of time. Maybe I'll have to skip through a little bit. All right. So let's now understand briefly. I think everyone will know about these things, but I would want to give you my own take on the types of machine learning there are. One is supervised, one is unsupervised, one is reinforcement. Supervised, as the name suggests, is that there is a supervisor. Okay. Now, so we are thinking all the time that the data is the supervisor. That is what we think. But data is here also. Data is here also. So what is so supervised about this? The reason that makes it supervised is, first let's understand supervised, and then I will connect the dots for you. Supervised machine learning works something like this. Let's say you want to build a system that can identify cats. So you would give all the cats pictures to it. So you are not just giving 1, 2, 3. We are not giving only 3 pictures. There is also another layer here you can see. Okay, we are giving a lot of cat pictures of this category. This is a cat species, which is different. This is like an Indian cat species. This is also sort of an Indian, that's what we see. And this is the bobby cat, the bobcat, which is not observed much here, maybe European breed. So we give all of this different categories of cats, but all are cats only. Okay. Now the machine is going to learn all of this, and it's ready now to get classified. So when we next give it a new set of data, that is the blue ones are the testing data, the orange ones here are the training data. So while we test, once the model is built and when we test, the system is able to classify and say that even though these two were different classes of cats, it still knows that it is a cat. It has observed something, some features. Okay, so these are the, whenever we give data, we have something called a feature vector, and one is the prediction vector. feature vector, prediction vector. All the data that you think matters for the building of the model. If you think you're collecting those data, that is all the features. You're adding the features of the cat and stuff, everything. Now, whatever you want to predict is the class here. In this particular case, it is a class. Whether it is a cat, whether it is a dog, what classes are here? Dog, cat, or maybe fish, if you want to add fish also here. So different kinds of classes. So what are the feature vectors? All the features of something having, like, let's say, does it have a tail, or does it have a canine teeth, and the face, the photo of it, right? And then the same thing moves for all. Fish, does it have a tail? No. Fish, does it have a canine teeth? Most of them, yes, but most of them, no. Some fish really do have sharp teeth. And the photos, the face, the photos of it is all given. And all of this now becomes a feature vector. All of that gets embedded in, and the model is built. Now, supervised machine learning has two kinds of problems that it can solve. One, it can classify, one it can regress. This is an example of classification. And if you want to apply supervised machine learning to predict the stock market, that is regression, because those data are not categorical data. The end result is not to say whether it is a cat, dog, or fish. The end result is to say what will be the stock market price after a certain date. There's a one number that we are requiring in regression. What is the next number, or a next number based on a different date? So we build an algebraic relationship between the feature vector and the prediction vector, right? That is in regression. You regress the values, and this is classification. But both of it, what do we have in reality? We have labels. This tail, the face, the color, the teeth. These are features. And why did you choose these features? Because you know something about this data. You know you can collect all these things about the data. You know these are the important features that can help you classify the data. So it is not just the data or the availability of data that makes a machine learning model supervised. It is the availability of labeled data. The moment you have a labeled data, automatically you can go and get consulting from the domain experts. Now, if you are a data scientist and if you work for finance and you have labeled data, you will get expertise from the domain expert who is expert in finance. If you are into medical imaging, you would want to go and get expertise from a doctor, or the specialist, the cardiologist, or the child specialist, or whoever it is. So the specialists are going to come and make sense, and then they will help you to decide which features are important, which features are not important. That is domain expertise. That is labeled data. That is supervised machine learning. But there is something else that is called unsupervised machine learning. Now, let's have a look. Let's have an example of this one first. Unlabeled data example. Let's say you have a tweet. On Twitter, you have a tweet. You just have a random photo. Okay, you have a tweet. You just have a random photo. You have a random audio recording. You have a random video. So you now need to label it. We don't still have any labels in there. Okay, we now need to develop a system where we can analyze the data and possibly ask certain questions and see whether it has been found or not. So we can judge the sentiment of the tweet. We can take a photo and say whether it contains a house or a car. We can take an audio recording and check whether a word football occurred in it. Or you can take a video and check whether there are weapons used in the video. So what are the possible labels that can come out? Positive or negative. Contains house and car, yes or no. These are the answers that come up, right? So these are the prediction vectors which have to be fed into the supervised machine learning model. Why? I'll tell you. When you say past data is the source of all machine learning and AI, the past data needs to contain the feature vectors like tail. For example, the dog example, tail and teeth, and let's say can fly and swim, right? So we have all this, let's say on these 4 features. Now, after that, the answer is here everything is yes, no, and then the final class. Now, if I say tail, yes, if I say teeth, yes, if I say can fly, no, if I say can swim, yes, then it is either a cat or a dog. I don't know whether cats can swim, but dog definitely. So I'm definitely putting a dog here. You have to give all these data. Now, dog, we cannot directly give dog there to the system. Okay. So we have to do something called discretization. So dog will become 1, cat will become 2, right? You actually put numbers to the classes and you discretize it and you put 1, 2, 3, 4 here. Now, I'll put 1, and if there is a fish, I'll put 3. So let's say teeth, tail, can fly, swim. And now tail, I'll say no. Teeth, I'll say no. Can fly, I'll say no. And then I'll say swim, yes. Then this will become 3. Now your system is going to learn not just this. It doesn't make any sense learning if you don't give this vector. This is the prediction vector. You have to give the whole thing to the system to learn. Then next time when you ask it, so the system will have like a millions of lines of data like this. And next time you ask something of whether something like this, what it is, it will then give a prediction saying based on all the things that you have trained me with, when you test it, it gives you a 3. It's supposed to give you a 3 if you've trained it well, if you've trained it with a lot of data, because this is similar to it, right? So this giving the entire label data, including the prediction vector, that is supervising the model. You're completely supervising the model. Okay. So if you don't have this, if you just stuck with this data, you don't know anything about the feature vector, the prediction vector. It happens in why I was telling you about the example where in astronomy, right? So no labeled data comes to you. We have to do all the analysis ourselves. So an example, a simpler example of that would be what is shown here. The raw input in unsupervised is an example I'm showing you here. Here in this case, the raw input is just a lot of figures like this. One is a red triangle, another one is a blue square, a green circle. The features that possibly you can extract out of this is, let's say, number of sides, next color, and yeah, that's it. If you can just do these 2, fine. Number of sides for sides and color for the circle would be 0 and green. You can again have to convert green into a class 1, 2, 3. So then for a square, it is going to be 4 and color will be something blue. So if you give all this, the output, the response from your machine learning model should be a direct classification of how many different types of classes there are. So you are, when you're using unsupervised machine learning, you are in a discovery mode. You are discovering the pattern. You don't actually know it. After discovering the pattern, you become a domain expert. This is the process of becoming a domain expert. This is a process of actually discovering patterns in a certain phenomena which we don't know anything about. This is where real research is. Okay, this is from an industrial domain expert who will come for supervised machine learning. Unsupervised is actually the haven of research. Okay, so you collect a lot of data, then you apply unsupervised machine learning. There are different models, there are different classes of unsupervised machine learning. So if you discover it, that is when you discover and you write a lot of research papers. Okay, there is no reward in writing research papers for supervised machine learning. Anybody can do that, even industry will be able to do it. But when you conduct an unsupervised machine learning, actually this is a lot of noise.
Participants, please mute your mic because some sound is coming from you. Some participants, you have unmuted your camera mic. Please mute them. Sir, it's okay now. Please continue.
Yes. Yeah. All right. So that is about the supervised and then the unsupervised. So if you just want another take on unsupervised, there's an example here. Let's say you give the system information about star, a rectangle, a triangle, square, and all of that. It will absorb all this data, convert it into, of course, the binary, and then the output of unsupervised is classification. It doesn't know that it is a star. Trust me on this. We don't label it. This labeling is for you to just to explain things to you. The machine doesn't care what it is called. The machine is not even fed what it is called. In fact, when we give a data like this, we will not even give labels like this. Star has so many sides and so many sides, comma, so many colors. No, we are not going to say star. We are only going to give side, and it is not even labeled. We'll just say 5, blue, 0, a green for circle, and 4 sides for blue. This is all we'll give, no labels. Okay, it will itself go and classify it by looking at the patterns. It will say, okay, there are so many of the things that you talked about, and if you have different kinds of 5 yellow, then there was another 5 black, then was another 5 pink. So it knows that 5, 5, 5 are common. So all these 5, maybe the colors are different, but the 5ness here, or whatever it is, the 5 points here, or 5 angles that it is making, right? So there is something common about these 5. So it is going to take that. Now there are 3 different kinds of circles. Let's say here, one circle was blue, one circle was red, one circle was. So all this information it is going to see and come up with its classification based on one common repeating pattern. So this is here in terms of here in the here, the repeating patterns are about the sides, but in most of the cases, in most of the unsupervised machine learning cases, we'll have repeating patterns or spatial patterns. So like, you have algorithms like k-means clustering. So it helps you to cluster the data which is actually spread out on the graph, and how close they are, how farther they are in terms of the Euclidean distance between the points. So that is unsupervised learning. Maybe I'm going a little faster. In usual case, I don't actually go so fast. But the truth of the fact is, unless you understand these things correctly, you will be doing a lot of looping, because Python and machine learning, everything is automated. If you know what you're doing, it is very easy to build models. But if you don't know, and if you don't spend enough time on the basics and enough meditation on the basics, you will not know. You'll be very uncomfortable actually while dealing with these things. Anyway, so next important thing is in machine learning, the types of machine learning is reinforcement learning. Now, in reinforcement learning, the idea here is, the whole gist is in the word itself. Reinforce. Reinforce means something is happening again and again. When do you do okay, regain or revolt, or you're doing something again and again. Regress, right? So reinforce directly relates to real-time activities. The model is actually being built in real time. Means the finished model is deployed, okay, but the process of building the model, again and again, one particular, there is the same ambient noise is coming. It's the same source of noise. Sir, it's a really
Sir,
Sorry, sir, for the all the disturbance coming up, but we're trying to put all the attendants on mute. Okay.
Sure.
Vijay, sir?
Yes, sir, I'm here. I'm trying to figure out a way where I can reduce the input to my ears.
Okay, so Sambhu sir, I suggest one mechanism. Sambhu sir, are you there?
Yes, sir. Yes, Ravi,
okay.
Sir.
So you have the option to, let's say, mute all, right?
Yes,
and ask participants, if anyone want to, let's say, ask, then he should raise the hand and you unmute, right? So you take the mute unmute capability along with you, instead of putting to the participant, so that our speaker can smoothly, let's say, deliver the information. Is that fine?
मैं तुम्हें बता उसकी डिटेलिंग में पहुंचाती हूँ और समझाती हूँ ठीक है
Okay.
Yes, sir. Yes, sir.
Yeah, I'm coming to you.
Sir, it is not possible now, it seems, according to my knowledge. While in the settings, they are supposed to do, organizers are supposed to do all these things, sir, I guess.
This is okay. Hopefully this part is very important, because this is like the culmination of everything. Okay, so hopefully we'll not have much more. Let's continue now that we have got some window of peace. Reinforcement learning is something where the process of building the model actually happens in real time. It doesn't mean that the model, we are not saying it because the model will be deployed in real time. All models can be deployed in real time. But in reinforcement learning, the process of building the model happens in real time. But here it is not in real time. No, we collect all the data and then we ask the system to connect an algebraic relation. Let's say, for example, you have age and you have salary. Okay, so age and salary has certain numbers, x1, x2, x3, x4, and salary y1, y2, y3, y4, and you plot this on x and y axis, and you have age x1, x2, x3, and you have salary y1, y2, y3, and you have all this data x1 comma y1, right? There is some data, some numbers over here, so together these numbers together come to us, and we get a plot on this 2D graph. Now we need to fit a curve for this. So what this curve is, there is actually an algebraic equation which can represent this curve, and that algebraic equation is made out of x and y. So that is an algebraic relation. So once you get the data, this is a static data, you build a curve, you fit a curve. That happens in supervised learning and unsupervised learning also. But in this reinforcement learning, this curve fitting happens in real time. Why? Why? Because no matter how much data you collect about certain events, you still don't have enough data that can compensate for all the variance and the bias that the system has. For example, if you want to train a robot dog, or I'll give you an example. Let's say we have this game. This is a Pac-Man game. We used to play this game. Okay. Now we used to, when we played this game, we were this, okay, this green color thing, this green color, this was human. You used to control using your arrow keys, and your work was to go ahead and eat of all this. Okay, and these were the ghosts, and this was controlled by the computer. That is, if you can recall, give me a hand raise if you recall this game. Give me a hand raise. Only 2 people remember this. Yes, absolutely. Yes, I'm confident now that people are listening and they are actually with the game, right? So now let's reverse this. How can you build a model? How can you build a system where this becomes the computer, and all the 4 people I saw first raising, no offense to all other people, I just saw 4 people raising their hands. Let's say all those 4 peoples now become ghost 1. I'm sorry, this is just an example, take it lightly. Ghost 3, ghost 4. Okay, now all of you are now controlling arrow keys, and you are behind this computer. Now it's the computer's work to go and eat off all this, and now you are using all your tactics to go and attack this. How can you, do you think you can build a system like this? Do you think you can train a computer to be you? If you want to train a computer to be you, you have to now use reinforcement learning, because every time there is a movement done by computer, you will have to tell the computer whether it did something right or it did something wrong. This is the future. This is the future. Reinforcement learning is the future. All money, all investments, if you want labs, if you want research, if you want awesome papers in Q1 journals, work on reinforcement learning, work on unsupervised learning, work on statistical methods. Okay, so these will get you amazing paper publications. Now, moving to the gist of it. So how does it happen? In reinforcement learning, coming to the simpler example, the input, we say the response from this is the input, an apple. The response from the machine says it's a mango. The feedback mechanism says wrong, it's an apple. The machine says noted, thanks. The next time, the reinforced response will be an apple. Now, if you want to put the same thing in terms of equations, you have an agent, you have an environment. The agent was, in this case, the agent was this Pac-Man, the PC man, Pac-Man, which was supposed to be the computer now, and we were supposed to train this Pac-Man to be as intelligent as humans. So that is the agent. And the environment is all the four ghosts who are constantly behind. There is something changing. So all this. So all that environmental observations are fed in to the agent. The agent does an action. Environment decides whether the action was good or bad. Depending on that, you reward the agent. The agent is even slowly building its own complex network, a complex model where it knows when it was rewarded and when it was punished. This reward and punishment again is converted into these vectors over here. So when you convert this into vectors, we call it cost function. Cost function in reinforcement learning is an algebraic relationship between the weights concerning the rewards and punishments, because it is just not whether you rewarded it or punished it. It's about how much was the reward, how big was the reward, and how big was the punishment. It is keeping a track of all of it. And then eventually people have built amazing games where now you can become the ghost and it will run around and it does a fantastic job out of it. And this is reinforcement learning itself is a very deep concept. It's a beautiful thing. We are from Certishort. We are also coming up about after a month. We are coming up with a workshop on proper reinforcement learning, but that is for an advanced student who already has enough experience with machine learning, AI, and deep learning. So we will let you know if anyone is interested in learning that. Anyway, so let's summarize the whole thing. Building machine learning models. What do you do with it? First, you have the initial data set. Okay. Let's say, do you have any doubts with supervised, unsupervised, or machine learning? Supervised, unsupervised, reinforcement learning. Anybody wants to send me a chat message, or if you want to raise a hand, and I can ask the organizer to unmute and you can ask me a question, so that if there is some interesting question, I can work on it, I can think about it and get back to you. Looks like everything is clear, straightforward. Okay, give me a hand, raise a hand if everything is fine, and I can just go to the next section. Perfect. Okay. So building the machine learning model, you have the initial data set. You can do two things with it. If you think your data is not from a good source, because I'll tell you why. The big companies spend a lot of money on first sourcing the right data. I'll tell you why. Because you must have heard of a company called McKinsey Consulting. McKinsey. This company takes about $1 million just to produce 2 or 3 pages of report for the client. Now, where are the millions spent? They have the right methodology to find the right kind of data and then actually give you the right report for a company like, let's say, Infosys or Wipro, who wants to decide whether they want to invest on a new, let's say, electrical vehicles. So they'll go and ask for the McKinsey, and McKinsey say, I'm looking to invest in this sector. Can you give me a 2, 3, 4 pages report which can help me decide? McKinsey is going to set up the data science experiment. It is going to take the initial data set. it is going to now do the exploratory data analysis where you explore, and here is all your inferential statistics which is going to be used. After that, once the exploration is done, you will know that a lot of data is going out of the charts. There is a lot of outliers in the data. There is a lot of missing numbers in the data, right? So when all this exploration is done, then you do the second step of data cleaning. Then you do data curation. Then you do remove redundant features. Redundant features means what? If in your data, if you have something like label, let's say you have a label called bird, then you also have the next label called fly. Okay, why do you want both bird and fly? If it is a bird, it can fly. Why you want to burden the system to again compute whether it can fly? This is redundant data. You remove that. Okay, so this is all the part of data cleaning process. Now once the whole thing is done, the pre-processed data is divided into 80 and 20. Whatever is data, if you have 10,000 points of data given to you, put 8,000 here, 80%. Okay, 80% of data use as training set, 20% of data use as testing set, because you don't want to train and test on the same data. That doesn't work. Okay, you as a professor, you will not set up, you'll not given you set up an examination, you'll not set up a paper in which the same examples are given. You use the same examples which you taught in your subject, right, to the students. That is not an examination at all. If you teach the same problem with the same numericals and then ask the same problem with the same numericals exam, that is not an exam at all. So that's the reason why we separate the data. 80% here, you train the model. There's a lot of other, it's a very deep subject. So I will not be able to explain everything in detail in one shot, but we'll give you different resources and options to study the whole thing. Hyperparameter optimizations are there, feature selection, feature engineering, a lot of stuff happens. And here, if you have all these different kinds of algorithms, decision learning, and nearest neighbors, and gradient boost methods, and support vector machines, there's a lot of algorithms that we can use. And once you get some model, then there are other steps. Again, you can do a cross validation of the model. If you're not convinced, if its model is not behaving properly, you can do a cross validation. And in the cross validation, you will come up and you say, if this 8,000 points of data was there, you will divide it into buckets of 1,000 points, each 8 buckets containing 1,000. And you'll apply model, you build a model separately for that 1,000. Right, and then after that you will test it, and you'll come out. You'll actually observe that on the 7 buckets your model was perfectly fitting, but one of the buckets, let's say the 4th bucket where you had 1,000 points, that is where the model is not fitting. That is where you are getting just about 30 or 40% accuracy. Now you can go back to your database and find out what happened in those 1,000 points. What was so different about those 1,000 points that your model is not fitting. You can give back that report, to McKinsey. Will get that report, and McKinsey will go back and give it to the sourcing company and say, these 1,000 points are either wrong, or we'll not pay you for it because it is not making any sense. It's rubbish. Or another inference can happen. Maybe something happened during that phase which is very important, right? So these kind of inferences will be drawn. And of course, that is where statistics comes in. So using statistical methods, you will now put forth an hypothesis and then prove it or disprove it. And after that, a report is generated. And once you sort of think that you've come up with a model, you'll go ahead and test it. Once you've evaluated it, you will then put it on cloud or wherever you want to put it and deploy it for the real world. Now, with this is the whole pipeline. This is how the pipeline is built in machine learning. The gist of it all is, whenever I was talking to you about these things here, the algorithms, support vector and decision trees and all, the whole idea is about finding that optimal solution for the given curve. And this is a 3D mesh of a relationship between phenomena which has these Q1 and Q2, and Q1, Q2 another function, a new function h based on q1 and q2, and all of this together gives you this plot, and this plot is actually the event. The whole event is actually seen as a 3D plot. If you want to build or fit a curve, you want to fit a curve in such a way that the slopes and the point at which you will achieve a global minimum or global maximum is highlighted. That's the cost function. So to build that cost function, we use a method called gradient descent. And the method of gradient descent is exemplified here in this picture. The gist of it is very simple. Gradient descent, by nature, by the inherent algorithm, it is devised in such a way that when the gradients slows down, this picture is actually a wrong representation. In fact, it should be like this. The step sizes slows down when the slope decreases. That is what it's a gradient descent. Otherwise, it would be just descent. Correct? Why it is gradient in nature? The gradient in nature is because it is taking into account the gradient here. So here the slope was of some value. So when it knows that there is certain slope here, so it will decide what is the next step size. So based on the next here slope here, it will decide what should be the next step size. So like this, it is going to, and then find out and come to that, and it will know that this is where the minimum cost of getting that combination, the minimum cost between these two relationship, the minimum cost is found here. The challenge, however, is not everything is as simple as that. This is an ideal case, but this one, if you see, this is actually a real case. And if in case, let's say you have, let's say our example was not about finding the minimum. Let's say our problem was finding the maximum. So you have, let's say the point starts from here, and if you're trying to find the maximum, this is one maximum and this is another maximum. And if you want to inspect, draw a line, and you can clearly see this is actually the global maximum. The problem with this the gradient descent, when it is trying to build that curve fitting, right? When I said it will fit a curve, this is how it will fit a curve, by finding these cost functions for every slope, finding the minimum slope for which you will fit the curve. So this is the local maximum, and this one is the global maximum. And directly applying some gradient descent or something, it is not going to guarantee you that you will always find the global maximum. So to find global maximum, then you'll have to start from different points, and then luckily, if you're lucky, it'll hit a global max, or you'll just end up with global minimum, the local maximum. Okay, if you're lucky, you'll get the global maximum. Otherwise, you'll just end up with the local maximum. So there are different ways to tackle it. There are different fields to tackle it, and one of the fields which helps you directly without helps you to avoid all these things. Now you'll understand why deep learning is required. To avoid all these problems, you'll come to deep learning. Okay, so in deep learning there is a lot, because we've already crossed our so can anyone tell me how much more time I can take? So based on that, I will shift to.
Sir, I think we are nearing the ending of the session, because the next session will start from 1:30. So
Okay.
still, and we need
Maybe
to give
another 10 minutes.
Yeah,
10
yeah,
minutes I'll end.
yeah, sure.
Okay, sir. All right. So key points is deep learning is used as an alternative for your classical machine learning models. And deep learning derives its methodology and derives its approach based on the neurons in the brain. So what neuroscientists observed was the neurons are connected to other neurons through axons. And axon is the one which carries the energy, the spark. So if there are, so basically what it says is it is actually true that if there is an event which is powerful enough to spark an idea or spark some thinking, spark some process in you, then there will be a set of neurons that will fire. So when many neurons fire together, that is actually learning. And a lot of millions of neurons firing together interconnected is actually the mind. Okay, so they have devised it, they've understood it, the whole thing is put together in place. Inside that, now they have created an exact replica of the neuron in terms of a computational unit. And inside that computational unit, you have many different things. So we don't really have that much amount of time to go into the whole activation function and all the things. But I have something interesting. Okay. So instead of that, let me go and open up. Let's go to this. This is called the neural network or the TensorFlow playground. Okay, TensorFlow playground is a Google sponsored playground where you can actually put a lot of, set up a deep learning network and see how the actual training is happening. But let me connect the dots for you quickly. Deep learning also has gradient descent involved, and the gradient descent that is being calculated is nothing but, here in this case, it's partial derivatives which tell you how a multivariable function changes as you tweak just one variable in its input. Okay, so of course, when multivariable functions change, when one variable is tweaked, that is your partial derivative, right? And then, of course, what is the derivative? You can just go find out and you get more sense of it. Now, this key function is, the key thing to remember is this calculus, which is there. If you really want to do calculus the way Newton or Leibniz explained the Taylor series and all, it is computationally expensive. It's very costly. It's expensive means it takes too much time, too much resources. Now that's why they came up with a very smart technique called autodiff. So it is an auto differentiator. So automatic differentiation, okay, AD. So this automatic differentiation, I'll show you where the differentiation happens. But this automatic differentiation is a set of steps. If done, it computes in a finite time and computes very fast. Now, this auto differentiations are embedded in the neurons that has been created. So each neuron with an embedded auto differentiator, of auto differentiation in machine. When you construct a lot of this is called a tensor. Okay, so Google's new technology that they gave out for deep learning, the TensorFlow library, actually consists of you creating neurons which has inbuilt auto differentiators. And one more important concept here is of the activation function. So here, if you go to the brain itself, I'll not go into the math of it, I'll just go here itself. When this neuron has to connect with another, let's say a neuron, if there is enough activation here, enough energy, then only it'll have enough energy to go and pass on and get the next neuron to fire. Then this is connected to another neuron. This has enough energy of its own, and then the input from here, then it will go and connect. So everywhere they've observed that there is certain conditional activation. There are certain conditions for these neurons to get activated. So they created the deep learning also using same kind of conditions. That is your activation function. Activation function. which has something called an LTU, linear threshold unit, right? So these threshold units are the ones which decide how many neurons get activated. So let's see that in action right away. Okay, so I've explained certain things. I'll explain all the other things here. What does it contain? Give me a hand if everyone is able to see the one which I showed you, TensorFlow Playground. Just give me a hand. Okay, great. Okay, great. All right, so let's first calmly observe what is in front of us. It looks complicated the first time you see, but I'll guide you through this. First thing, let's look at the left column. Here, play button. Once you start playing, something starts. So it is the number of iterations. The number of times the input and the output have interacted and they have shared information to build these activation functions. Number of times, 38 times has elapsed already. Okay, that is an epoch. At what epoch did we achieve the final model? So it's a measurement of time. We cannot say seconds. We cannot say how many hours. It doesn't work like that. We measure the model's performance in terms of how many epochs it took. Okay, so it's a measurement performance. Next, the data set is here. You have 4 different data sets. Now, usually you're used to looking at data set as an Excel sheet or something, but here this is also an Excel sheet, but this is a visual representation of that Excel sheet. So what this Excel sheet actually contains is, okay, I cannot draw on this. So let me grab my other pen. Okay, so this let's say this point here. Okay, what this says, this point is -2 and somewhere 1.5. Okay. Okay, I'm sorry, I don't draw straight lines. Okay, 1.5 comma -2 is this point. In Excel sheet, it is represented like this. When you put it in graph, it is represented like this. So all this is your given data. What it says, this minus 1.5 comma -2 is blue, and another, let's say, -2 and -1 is also blue, and it'll next say -4 and 3.5 is orange, and so on and so forth for a lot of data. So this is what it says. With that in mind, these are different kinds of data sets which you have here. So this is a simple data set. We can now set up a neural network where we are going to add a lot of neurons, hidden layers in between, and each of the hidden layer has the neuron which contains a threshold unit inside. That threshold unit is the activation function. There is a function which actually calculates whether this particular neuron should fire or not. 2 questions happen. Whether should fire, if yes, how much is the value of its existence? See, these 2 questions are answered. Should it fire? Decided by activation function. Activation. How much is the value? Decided by weights given to its presence or to its activation. Who is giving the weights? When it's moving, because this is the input data and this is the labeled, the feature. This is the feature vector, this is the prediction vector. Okay, so when the feature vector is sending out some suppositions like what it is supposing here, it is supposing here that all the points on the left side are orange and all the points on the right side are blue. This is its supposition. Now it will take this level and the other hidden layers are going to expand, and they will take some input from this X1 and it will give out its own assumptions. It will change it. It will say, no, I'm thinking all the ones which are diagonally onto the top are orange, diagonally onto the bottom are blue. This will change. This will say, no, I'm totally ulta. And this will say, no, I'm going to change the diagonal itself. I'm going to move from it'll go to the principal diagonal. It was the secondary diagonal, the principal diagonal. And this will say, no, I'll go with what X2 is saying. I think probably X2 is right? So these, what are you building here? You're building gamblers. This is my own way of understanding, because I feel all these hidden layers are actually gamblers. They're all gambling. Now, your deep learning's work is to give a value to the gamblers. So let's build this model and see what's happening. I built a random structure. It's not even, yeah, it actually achieved a model. Okay, it has finally achieved a model. It has finally got a model which can correctly identify. Now, see how the suppositions change from this end to this end, and from here to here. There were two different cases which this one says that everything in the center, everything around was orange, and everything in the center was blue, right? This one was the ulta, this one was the other way around. So there are different variations which happen, and finally the one which is getting it right is being rewarded. Weight is 2.2. The one which is getting it wrong is punished. Weight is minus 0.7. The same way, now once this gets a rating, it also has the ability to rate who told it so and so. Like it has taken the cue from here, so it will give back a weightage. So these giving back weightages, this is being calculated every step. A gradient descent algorithm is working, calculating, and that is your auto diff working backwards. Okay, so this is auto diff, which is working backwards, and this auto diff working backwards is actually called your back propagation. And every time inside there is an activation function which is first decided here. This is activation functions are of many kinds. There is an activation function tan h, ReLU, sigmoid, different kinds of activation function. All these are nothing but an extension of your, I hope you remember this step function. It is 0 if it is 0, and it is if it is 1 if it is slightly above 0. That's what a step function did, right? But the data sets that we deal with in normal situations, they are not as easy as this. So because of the non-linearity of the nature, you cannot use the step function, right? It will be oversimplification of the problem. You cannot use a step function. So you have different activation functions for that: ReLU, tan h, sigmoid, linear. Go check out what it means in actual mathematical language. You will see the variables there, and you will try to make sense of what it actually is doing. Basically, all you have to figure out in activation function is when is it 0, when it is 1, because it needs to be activated, right? Each cell has to be activated. When is it 0, and in what conditions it becomes 1. So if you get this gist, you will understand activation function. Now, learning rate, this is one more concept which you have to understand. Learning rate is when I was teaching you about types of machine learning. Yeah, this is the learning rate. Same thing applies everywhere. The principles of machine learning is always the same. Learning rate is here. See, I was telling you gradient descent. It decides the step size, right? So this step size initially, these step sizes, it doesn't work like a gradient descent problem here. So when you're doing a learning rate, it actually decides a constant step size. So if you decide on a step size which is so large, see, one hop, the second hop, the third hop, means you have missed the global minimum, correct? So if you make it smaller, so you will actually hit the global minimum. So this learning rate is set to this. There's another mechanism to actually set it. Slightly, I'm off time, so I'll not be able to explain how it is set. But this is the concept of learning rate. You have to have, you cannot have two less, you cannot have two more. Two less means your model will never converge. It will be too slow. Too high means your model will converge, but it will never give you the right result. Okay, so this is it. So you have different kinds of data. Go and go to just Google TensorFlow Playground and play around with this. And I'll give you my email ID if you have any doubts on that, anything that you require. I'm most happy to give you the insights into it. And finally, I would like to close this session with the closing remarks. Key points to master machine learning. When I say machine learning, data analytics, AI, deep learning, everything is on the same. Key points. First, understand statistics, because it is just not about the numbers. Inferential statistics help us to measure how true our model can be, because inferential statistics is about devising mistake here. Devising a number for trust, that is called the estimation, the trust in your model. Now, next, after that, you need to be hands-on with Python, because the whole pipeline is set up, and Python has a lot of inbuilt libraries which are ready to use. Okay, it's very easy. But the problem is when the Python gives you a function to use, you will have certain arguments inside it, and arguments will say, okay, how much learning rate you want to set, and what kind of activation function you want to use. They've made it automated, but who decides what is the learning rate, what is the activation, and how much is the weight that you want to put? That comes from domain expertise, right? That comes from expertise. So that is what why I tell you that you have to understand the depth of stats and the depth of algorithms. So once you're done with that, it's pretty much straightforward. And then you have to also have an appreciation for linear algebra, because once it goes to the image processing, neural networks, natural language processing and all that, it is not the same algebra that we are talking about in linear regression. It is linear algebra. They have linearized it. And the hint to take from linear algebra, it's a little too much if I start that. And dimensionality reduction is very important. Please take a screenshot of this if you really want. This is the whole thing. And feature engineering. Yet feature engineering itself is a haven for writing good papers, because you do a lot of feature engineering, and one of the good set of features that you can engineer out for a particular kind of phenomena, that itself can become a research paper. It's a beautiful thing. And performance measures, of course, training and testing and cross validations and all that are important. And deep learning, complete mastery of that. And after that, if you are from industry, then deployment of machine learning on cloud is something which is the trending thing right away. Okay, so domains where you can apply, everything will be covered in the subsequent FDP sessions. And yeah, for researchers, statistics is very important. I'll tell you why. When writing research papers on AI and machine learning involving large amount of data, estimates and confidence intervals have to be shown. Simply, you cannot just draw some data, draw some inference, because most of the papers get registered because you don't follow the right process of handling data. Whoever is doing an estimate, whoever is looking at your machine learning and AI, they're all statisticians. The first thing they want to see is what is your null hypothesis, what is your alternate hypothesis, what is your estimate, what is the confidence intervals, and what have you proved. Like, this is what they'll see. So you have to be able to show that the samples taken actually belongs to some population using the central limit theorem. It's a part of statistics. Go please check this out, central limit theorem and what it says. And must clearly state the null hypothesis, alternative hypothesis, then build a machine learning model, demonstrate which of the hypotheses of yours was right, then compare the statistical estimates with machine learning models result. So, okay, this was just, I wrote this down as something which I wanted to add at the end. And of course, as from Satishat, we are from Satishat, and we are coming up with these two amazing boot camps. If anyone is interested, do let us know. And one is called The Art of Statistics for Machine Learning Engineers. Another one is Proper Machine Learning and Artificial Intelligence, where we cover everything in depth. So if you want to learn more about it and get some attractive coupon codes for it, especially for this FDP the attendees. So you can just write to us at learn@certishort.com, and there'll be an attractive coupon code for all the ATAL FDP attendees on applied machine learning conducted by MUJ. All right. With that, I end this presentation, and thank you so much for your time. And I'm really sorry if there's a lot of mistakes and noise that happens. Hopefully, the first session is always like that, and they'll do the necessary corrections and arrangements next time. Thank you so much, people. Thank you so much. Give me a hands, please, if things are all clear and everything is cool.
Yes, sir.
Thank you, sir.
Thank you, Vijay sir, for your full session. Participants, if you have any question, you can put on chat, and
Chat probably still
at
disabled.
least some of. So, anyone having any question other than that, and this participants who are not having any query, they can lower their hand. And if you are still holding your hand, I'll give you the. Okay, so let's see. I still have, so I'll give Veerbhadrappa some access to the microphone. So I'm allowing his microphone. If you want, all those whose hands are up, I'm giving all of you the microphone access. If you want to ask any question, you can put up.
Yes, sir. Yeah, I'm listening.
Yeah, I think I'll just allow mic for all those whose hands are up.
Okay.
I think so all of your mics are available. So if you want to put up any question, if you have any query, you can ask. Vijay sir would be happy to answer them. Okay, so there is one question in the chat section.
Yes, sir. Chat,
So,
but I'm not able to see the chat.
the question is, can we combine machine learning and deep learning techniques for classification? So the question is, if we can combine machine learning and deep learning techniques for classification.
No, I don't actually understand what is this one, because machine learning, deep learning are same. The methodology, when it's like asking. I earlier thought it's the same, but now when I think about this question, I can see where it can actually help. Because one important thing about machine learning is it is a white box treatment. You actually can see what is happening. Once the machine model is built, you can see what is happening. But in deep learning, it will give you finest of the answers, but you don't know what is happening because everything is black inside, activation functions. And so machine learning and deep learning, if you combine, I'm not understanding the context. Here also you will give data, here also you will give data, and the same principles of data science is applied. Only thing is the models developed here are using classical methods, and models developed here are using deep learning methods or the new activation function methods. So when you combine it, in what stage will you combine it? If you just have data here, just have data here. Once you give the model, it'll generate an algebraic relationship. Here also it will generate an algebraic relationship, only that relationship is based on the algebra of your activation functions. So it doesn't make sense to me as yet as to how you will combine ML and DL, because it's like you want to travel from here to some place and you have an option to travel by car and plane. So you will travel halfway through car and the other half through plane. That doesn't work like this here. You cannot do halfway through machine learning and halfway through deep learning. How? I'll tell you. It's like going in the plane. Okay. So if you start from this place and start traveling from this place to this place in an airplane, you cannot decide whether, you cannot ask me a question whether halfway can I transfer from an airplane to an helicopter. It's just set. Once you start using deep learning, you use deep learning. When you start using machine learning, you use machine learning. You start with an helicopter, you end with, you get down on an helicopter. You start with an aircraft or a jet, you end with an engine. So that's how it is.
Yes, so there is an addition to this. The participants is saying that the features are extracted in ML. So is it the same thing is also done for deep learning?
Yes. Yes. You extract the feature, which means that you have good features with you. You have some methodology. You have some domain expertise that you have got. So you've extracted the right features that you want to use after doing all the data pre-processing, feature engineering, everything. And after that, use those features for deep learning. But what happens is when you, this machine learning requires all of this, the feature extraction and all this. Deep learning, it's like, it just take all this without even you extracting any features. You can just build a deep learning model. But that's up to you. But I would suggest you extract the features and then use deep learning model to get better results. Basically, the difference is this is better. Okay. This is like an aircraft. Actually, you can ride an aircraft, but you'll never get to, you can travel in an aircraft, but you will never get to drive it. Only very few people will get to drive it. But machine learning is like your car. You can also drive, and sometimes you can call for a cab also and get it. But aircrafts is you can never know what is happening inside. There is a whole field of research which is going on to create or completely understand how deep learning is actually able to get that models. This is better. Same techniques that you use in machine learning, feature extraction, feature engineering, do everything. 80-20, here also you should do 80-20. Same thing. It is just another way of doing it. That's it. Is there any other question? I hope it answered this. I hope this question was clear. The same thing. Machine learning and deep learning are the same in terms
Yes,
of.
yes, it has been answered. The participant is, I think, related. Yes, sir. So I think then we can end this session. Thank you again very much, Vijay sir.
Thank you, sir. Thank you so much.
Yeah.
You can of course write to me at learn@certishort.com. I'll definitely be able to help.
Sure, sure.
Thank you, sir.
Thank you.
Okay, so
All right.
participants.
Thank you.
Yeah, Vijay sir. Would you like
Yes,
to say?
I was just thanking all the participants for their the involvement, the constant hand raise. It helps us a lot as when we are teaching. It helps us a lot to be involved and stuff. So thank you very much, people. I hope you had a great time. Sir,
Okay.
may I sign off with your permission?
Sure, sir. Thank you so much, sir. Thank you.
Thank you all. Thank you, people.
And participants, thank you for attending the first session. Please fill the attendance form and the feedback form that has been, the link has been shared in the chat group. Okay, so please try to fill it over, compulsorily, mandatorily fill the form over there. Okay, so and then our next session will start from 1:30. Okay, our next session. So we hope to get you back by 1:30. Thank you so much.